Welcome back, AP Calc BC students. We're going to take a look at our second video that covers topic 10.6. We're going to switch our focus over a little bit and introduce a new kind of comparison test called the limit comparison test. Hopefully you've already watched the first video that covered the direct comparison test. Let's look and see how this one plays out. Now, often it says a series will closely resemble a p-series, or maybe it resembles a geometric series. But the problem is that you have a really difficult time establishing a term-by-term comparison that will allow you to use the direct comparison test. For example, you've got a series, you think about another series that looks like it, but yet you can't figure out which airplane is on top of which because there's so many complicated pieces inside of that nth term expression. Well, if that happens, then it's probably likely that you want to steer clear of the direct comparison test, and you might want to try the limit comparison test. Well, what does this limit comparison test say? Well, it says, suppose that you have a series that's given to you, and let's just say for the sake of argument that a sub n is the given nth term expression after the summation in the problem that you're trying to solve. So that nth term expression, you have to make sure that it always contains positive terms. If it does, then this is going to be a pretty decent test to investigate. Then you're going to find another series that looks like it, where it also has positive terms among its members. All you have to do for the limit comparison test is just take the limit of your given series divided by the one that you're making up. So you take the nth term expression of the given problem, divide it by the one that you're comparing it to. And if the answer to that is L, where L is finite and positive, what that means is that those two series will do the same thing. So again, it's important to note, let's say that the summation of A of sub n is given. This is what you're comparing to. Obviously, what you compared it to, you have to know what it does, right? So we know its behavior. Then whatever the summation of Bn does, the summation of An will do, as long as the limit of this quotient is some finite and positive number. Now, you might be wondering, do you have to put the A sub n on top? Think about it. If you put the A sub n on bottom, won't the result still be finite and positive? Let's say that you got 5 one way, 1/5 the other way. It's still a finite positive L. For the sake of being confused in my class, I will always put the given function summation expression A sub n on top. All right, let's take a look and see how this thing works. So here's our example 2. It says, show that the following general harmonic series diverges. Well, you talked a little bit about the harmonic series in a previous video. What we have here is the general harmonic, just meaning that it might have a coefficient in front of that n. Maybe we add a b, a positive or a negative b, but it's still going to interact as a harmonic series. And so we know that this should diverge, but let's double check. So what you're going to do first of all is decide what are you going to compare this series to. And I know that sometimes this is still the troublesome part because you have a very certain degree of freedom here. And you must understand that you could be working your homework with a friend and you two might pick two different series to compare it to, and you're both going to be fine. You're both going to achieve the same answer. So you've got some flexibility here. I'm going to try to choose the series that's probably the most commonly used in each case. So for example, in this particular instance, I really think that if we just kind of cut away the A and the B, because to me, it's that n value that's really dictating what's happening because n is moving from 1 to infinity. And I would be more than happy to compare to this because I know that this diverges, right? This is the divergent harmonic series or divergent P series. Now, I'm hoping as I continue this problem that my limit that I set up will produce a finite positive answer. So let's see what happens. So we go to the next step and we take the limit as n approaches infinity of, and remember, I'm going to take my original problem, 1 over an plus b, so that's like the a sub n, and I'm going to divide that by the series that I've compared it to, or at least the nth term expression of that series, called b sub n, and I'm going to put that as 1 over n in that denominator. Okay, so what is this limit? Well, that's a good question. This is a very hideous looking fraction, so I need to fix it. So I will multiply by the reciprocal, which basically puts an n on top and an an plus b on the bottom. And then I look at this a little bit further and I see that, yep, I do have powers of 1 for n on the top and bottom. So I could just divide out their coefficients, 1 divided by a. And what do I know about 1 divided by a? Well, if a is a positive value greater than 0, then I have something that's certainly finite and positive. So basically, the behavior of my given series is going to match the behavior of my compared series. So therefore, I'm going to diverge. And I'll tell you what I am going to do here. It probably looks better. Let's go ahead and spell this out a little bit more clearly. Which series diverges? Let's state the one that we were looking at. All right. Now, it's likely you might look at this and think, hey, I don't mind this test. This test isn't so bad. I don't have to worry about comparing one series to the other in terms of which one's bigger or smaller. I don't have to fly any airplanes. You don't need a pilot's license to do these problems. Let's go with that. Maybe we might be onto something and these problems might be a little bit more enjoyable. So some helpful examples in choosing appropriate P series. Well, a lot of times you do have a P series kind of vibe happening with the original series. So this just gives you an idea. In the general series column, that might be your original problem. In the comparison series column, that might be a good idea to compare to. So you can see that if you've got something like 1 over 3n squared minus 4n plus 5, you can just rip away the things that don't seem to be too important and just focus on the 1 over n squared, and you would find out by the limit comparison test that both of those series would indeed converge. Something like 1 over the square root of 3n minus 2, rip away the 3 and the 2 and just think about comparing it to 1 over the square root of n. In this case, you're going to have two divergent series. Something like n squared minus 10 over 4 to the 5th plus n cubed, again, kind of think about getting rid of the minus 10 and the plus n cubed. You really don't need that 4 in the grand scheme of things. So n squared over n to the 5th is going to behave like 1 over n cubed. And if you pushed forward to using the limit comparison test, you would find that both of those series converge. So maybe that could help a little bit. And let's see if we can use those to our advantage in working through example 3. Determine the convergence or divergence of these two. So the summation, radical n over n squared plus 1. So the very first thing, what are we going to compare this to? Well, if I look at this, plus 1, I could probably ignore him. He's not really significant down the line when n gets to be really big. So I could just compare this to the summation as n goes from 1 to infinity of square root of n, or n to the half, over n squared, which then in turn means if I do decide to simplify this and subtract those exponents, this is really just 1 over n to the 3/2 power. Now it's highly important that you understand the behavior of this series and that this is indeed a convergent P series. Now, If you have to think about that for a second, that's okay. But if you really are lost on how this is a convergent p-series, I highly recommend that you might kind of go back, look at some 10.5 material again over p-series. The p is 3/2. That's greater than 1. That's why you know that this converges. So here we go. Let's do our limit. So we're going to take the limit as n approaches infinity of the square root of n divided by n squared plus 1, all divided by 1 over n to the 3/2 power. Well, that limit is quite the nightmare, so why don't we multiply by its reciprocal? In the meantime, I might call that square root of n an n to the 1/2 to kind of set the tone for what's about to happen. Okay, and I'll call n to the 3/2 a denominator of 1 after I flip it. And if I simplify this just a little bit more, essentially multiplying the numerators together, n to the 1/2 times n to the 3/2 is n to the 4/2, which is n squared. And my denominator remains n squared plus 1. Well, that limit is certainly equivalent to 1 because the 2's match. 1 is, believe it or not, finite, right? Finite meaning it's a numerical value. It's not infinity, and positive. So you got to make sure that you don't get 0 for an answer or a negative number for an answer, because if that's the case, then you can't make any conclusions about the limit comparison test. So therefore, the behavior of our given series, which was the square root n, over n squared plus 1, is going to converge. Hopefully this is making some sense. All right, now I know I've infringed a little bit on my part B, so what I'm going to do is just kind of get rid of this amount of work. I probably should have written that on the next line below. And let's see if we can do the same thing for our part B. Part B's a little bit busier. You've got a lot of things going on, but again, your job is to think of what you can compare this to. If we get rid of the things that don't really seem to matter, well, what are those things? I don't think that plus 1 in the grand scheme of things really makes much difference. Multiplying this n cubed by 4 really is rather insignificant by the time a really large n gets raised to the 3rd power. Up on top, believe it or not, multiplying by n, fairly insignificant. After 2 is raised to a really large power. 2 to the n really dictates how the top grows rather than multiplying just by a plain old n. Now, it's not probably unlikely that a lot of students would stop here and use this as their comparison. And I would invite you to maybe pause the video and off to the side somewhere, try the limit comparison test using that, because you get something that is a bit bothersome. You should get something that is infinite. You get infinity as your limit. And if you were to try to conclude using the limit comparison test, well, we couldn't, because we have to get something that's finite and positive. So what I'm going to do is go one little step farther with this problem, and I'm going to choose the correct piece to compare it with. And again, in the grand scheme of things, 2 to the n is going to grow faster than n to the 3rd. So I could actually get rid of him and really just compare this to 2 to the nth power. And I know that 2 to the nth power is indeed a divergent, I almost wrote the wrong word there, everyone. This is a divergent geometric series, right? See how the R value is 2 and the power n is attached? So let's see how the limit comparison test works here. Hopefully we'll get a result that's finite and positive. So we take the limit, and I better cover these so I can get the correct expression here. So I'm taking my original nth term expression, I call that a sub n, and I'm going to divide that by my b sub n, which surprisingly was just 2 to the nth power. Well, let's go ahead and multiply by the reciprocal here. And we end up with n times 2 to the n over 4n cubed plus 1 times, flip and get 1 over 2 to the nth there. As you can see, these guys will cancel. And then if I do compare the degree of the top with the degree of the bottom, I end up with n to the first over 4n to the third, which isn't good, right? That's equal to 0. And 0 is not finite. Well, it is finite, but it's not positive. So it's a little bit troublesome here. So if you think about this, this is kind of unusual. It's like, what do we wish might be right here in order for us to be able to have a definitive conclusion? If I want this n cubed in this denominator, then boy, wouldn't I want an n cubed up there in that numerator? So the trick sometimes is to work backwards. What if I had an n squared there? Wouldn't that produce an n to the third on top? And then I would end up with a limit of 1/4. Hopefully you all can see. Well, if that was going to happen, then by golly, I would need a 2 to the nth over n squared here, which means my comparison series should have been 2 to the nth over n squared here. Well, that's all great and everything, but you've got to make sure that this series here is still going to be divergent. I know it's not a geometric series, but it is still divergent. And the reason that we know that is because this 2 to the nth is going to overtake n squared. A lot of times if students are confused by that, I just simply have you list out a little table with those terms, let n grow really as big as you need it to grow, and then just compute these values. 2 to the n. 2 to the first is 2, 2 to the second is 4, 2 to the third is 8, 2 to the fourth is 16, 2 to the fifth is 32. N squared. 1 squared is 1, 2 squared is 4. Yeah, they look about the same. 3 squared is 9. Yeah, okay, maybe n squared is a little bit bigger. 4 squared is 6. Ooh, it's a tie right there. 5 squared, 25. Well, by the time you get here, the 2 to the n is going to be bigger. And okay, maybe I could go one more just to prove you. In fact, hey, I'm like, right there, right there. Let's see if you're going to be the same or even bigger. 2 to the 6th is going to be 64. Yep, that seems right. And then 6 squared is 36. So you can see that at this point here, the value for the n squared is just going to get completely overtaken by the 2 to the n. So there's no question that this diverges. Now you can probably prove this a variety of ways. I think the nth term test is the best, right? Divergent by basically taking the limit of that expression and using the nth term test for divergence. And so we've kind of worked backwards to get the result that we want. And so we can make the claim, therefore, that the summation of our original expression, n times 2 to the n over 4n cubed plus 1, is definitely going to diverge. Now, possibly at the beginning, maybe some of you were thinking, well, wait a minute, if you said to get rid of the 1 and get rid of the 4, couldn't you have thought about canceling the n and the n cubed to get 2 to the n over n squared? Great maneuver. Because if we did that, that would lead us to this exact comparison. But I wanted to show you just a strategy that you could use that kind of helps you work backwards to get the result that you want. All right. The only other thing I wanted to share with you here is this little known test. It's called the polynomial test. Sometimes in the history of great rock and roll music, there's always this person that was a part of the band who never really got quite the notoriety, like the Beatles and Pete Best, for example. Well, the polynomial test is like the Pete Best of the convergence test. It's never addressed on the AP Calculus exam. It doesn't really proclaim itself to be one of the big 9 comparison tests in any calculus textbook, but it could be something that you could use to help you a bit. It says the following is just a special case of the comparison tests. It's called the polynomial test, not tested on the BC exam, not referenced, but it has some great insight. Basically, if you have P sub n and Q sub n of polynomials of degree j and k respectively, think of P of n and Q of n as being our A sub n's and our B sub n. It's the same idea, right? Except we're going to think of these as being maybe continuous polynomial functions. Well, the P has a degree of j and the Q has a degree of k. And so we have to think of that throughout. Basically, it says if this numerator exponent is smaller than the denominator minus 1, then we have a convergent situation. If the numerator exponent is either bigger or equal to the denominator minus 1, then you have a divergent situation. And remember that these can only work when you've got polynomials. I'll be honest, most of my students think, one more test, no thank you. And they just rely on the limit comparison test, even though it might take a few steps. But if you're looking at some multiple choice questions where you don't have to be so meticulous and show your work, and you have an understanding of this, it can be a little bit of a time saver. So my advice to you is to use the limit comparison test as you start to work through the skill builder, but maybe when you finish a problem that has polynomials top and bottom, kind of go back and look at this and see if it does ring true, and that might help it kind of, I don't know, find its way into your memory a little bit so that you might be able to use it in the future. Anyway, I hope this helps. This concludes our 10.6. We'll see you next time with topic 10.7 as we move into the wonderful, wonderful world of the alternating series. We'll see you next time.